So okay, in this video we're going to discuss the concept of random variables. Now, this is a quite a difficult, quite subtle to understand concept, and I think it doesn't help what the name is, random variables. So I want to motivate what a random variable is, and the purpose of random variables is all about the fact that if you consider a probability space, so let's just recall what a probability space is. So if you have an arbitrary probability space with your sample space, your set of events, and your probability measure, at the moment it's a very abstract mathematical object. You have a set with outcomes, and these outcomes could be anything, anything at all. So it's quite an abstract structure at the moment. So let's, for instance, consider the probability space for flipping a coin. There are two outcomes to flipping a coin. It could be heads or tails, presuming it doesn't land on its side. And those are each the set. So that's the sample space. The set of events is then you have the set, or well, you have the set. It's basically the power set. You have the empty set, the event that you get a heads. The event that you get a tail, or the event that both happen, head or a tail. Okay, so that's the set of events, and to each of these we ascribe a probability. So let's say it's not exactly a fair coin, and it assigns a probability p to heads, and a probability 1 minus p to tails, and of course this set is given the probability 1, and this set is given the probability 0, because this is the whole sample space and this is the empty set. Okay, so there's our probability space, and at the moment it's labelled in terms of these concepts of head and tail. But consider something, consider this sample space here. We have just 0 and 1, so a subset of the real line. And let's have the set of events as being equal to the empty set, the set containing 0, the set containing 1, and the set containing 0 and 1. And let's ascribe probability. So the probability of the empty set is 0, the probability of 0 can be, we'll give it p, the probability of 1 can be 1 minus p, and the probability of the whole space is obviously 1. So look at these two look at these two probability spaces. What do you notice? That they are utterly the same, other than the fact that the actual sample space is different. This is just 0 and 1 in here, two silly numbers, and this is some actual outcomes here, heads and tails. But as far as the axioms of probability are concerned, as far as its probability space structure, as far as all of its structure is concerned, as far as all the mathematical structure which is relevant to probability is concerned, they are the same. Now this is a really, really important concept here, that these two things are the same. I could relabel this sample space here. I could relabel heads as being 0, and I could relabel tails as 1. I could set up a bijection, a map from here to here, and the probability space structure is the same then. What it is if you've seen abstract algebra, if you've done group isomorphisms, it's exactly the same. A group isomorphism is where you have an algebraic equivalent of this, where two groups are utterly the same up to the fact that the elements of the group have different names. But as far as all the algebraic structure is concerned, they are the same group. In this case, we have two probability spaces that are utterly the same as far as the probability space structure is concerned, other than the fact that the elements of the sample space are called something different. And through a relabeling, I can turn them into this one. So this is what would, if this wasn't probability, this would be called an isomorphism. But this is probability, and this goes back hundreds of years before the concept of isomorphism and abstract algebra had come along. So instead, this function that maps maps the probability space heads and tails onto this standard probability space. So basically we could come up with more probability spaces that are similar to this. So for instance, the probability that I missed my plane and the probability that I don't miss my plane. So missed plane, get on plane. This is a probability space, and again it has exactly the same probability space here. You have the set of events, which is that nothing happens, that I get on my plane, that I don't get on my plane, miss plane, or that I get on the plane or I miss the plane. So let me bring this up. Get on plane, or miss plane. So that's a set of events, and again you can ascribe probabilities to it. So let's say the probability that I miss the plane is p, and the probability that I don't miss the plane is 1 minus p, and then we've got 0, 1. So again, this is the exact same probability space. Well, it's not the exact same probability space. It's the exact same probability space as far as the structure of probability is concerned, but it's all that's different is that the actual specific outcomes are different. So the names, it's a different labeling. So basically, we are going to pick this one as our standard representative for every possible sort of probability space you can come up with this same structure, just different names for the outcomes. So different outcomes, but with the same probability space structure. They're all going to be represented by this one. Why this one? Because the elements here are real numbers. So we want to pick as our standard representative of all of these probability spaces. We want to pick one that has the real numbers. As outcomes. So this standard representative is called, for this case, all of these distributions here, don't use the word distribution, we haven't defined that yet. I'm not going to use distribution again in this video. For all of these probability spaces, I was using it wrong anyway, for all of these probability spaces here, they all have the same structure. Of course, not every probability space has the same structure. Of course, if you put a probability space with 3 elements in, that's not going to be the same structure as these. I.e., you can't relabel this to turn it into one of these. However, all of these are effectively the same, and they are all said to have the Bernoulli. This standard one here, this Bernoulli, this standard representative for all of these probability spaces is called the Bernoulli P space. And the functions, these functions that map, these relabelings, if you like, that map any old probability space with whatever old outcomes onto this standard one, they are known, these functions are random variables. Now, random variables, why have we named a function, this function which is describing this isomorphism between these two probability spaces? Why have we called it a random variable? It seems like a really stupid name. It's not what we expect a random variable to be. We don't expect it to be a function. And the reason is, random variables was a word used years before probability was axiomatized. And when they axiomatized it, they decided that the best way of using that word would be then to describe it as these isomorphisms between probability spaces. These functions mapping, relabeling one probability space and turning it into this standard one. But the motivation for where it came from was that it's really, these are the random variables here. All of these different probability spaces, so this head and tail one over here, or this plane one, or whatever other ones you can think of that have this same probability, this same really, really simple Bernoulli P space, probability space. So P space because you're assigning probability P to 0 and 1 minus P to 1. Any probability space that has that structure, all of them are effectively random. They could have the actual outcomes that can be represented by 0 and 1, that can be relabeled onto 0 and 1, are completely random, and that's where the term random variable comes from. It's describing all of these probability spaces, all of these random probability spaces that are all effectively equivalent, as far as the mathematical structure is concerned, to this standard one in terms of the real numbers. So a generalization of the concept of random variables to other ones, because obviously not every probability space can be mapped onto this and is the same as this. In fact, we need to do something more prior to this, because just as in algebra you have the concept of a homomorphism, you're going to have a concept of a homomorphism here, which is a generalization of the isomorphism. So let me give you another example of where we're going to set up something very similar to an isomorphism, but it's slightly more subtle. This is more difficult to understand than the concept of an isomorphism. So let's take the probability space that you flip a coin twice. So you flip a coin twice, so the outcomes you can get a head and then a tail, or you can get a head and then a head. You can get a tail and then a tail, or you can get a tail and then a head. So this probability space is bigger, and again we have a set of events. I'm not going to list them this time because it's much more events this time. Every possible subset of this, which is much bigger and will take a lot longer to list. But what I want you to see is that in some sense this is still the same as that other Bernoulli space, that I showed you in the last example. So if we look at the Bernoulli space 0, 1, and I'm going to put the light on because the video doesn't look very good quality at the moment. Let's see if that's improved it. Now I've got those lines going across, sort of waves. Not great. Don't know whether I prefer it with the light on or the light off. Is it just because it's zoomed in though? No, it's not. Okay, we'll go back in. Right, I'm going to turn the light off so we don't have those lines spreading across it. And I'll try and get more natural light in, see if that is better. Okay, so let's continue our discussion of probability space, and I would actually like this zoomed out a bit more so that you can see both of them at the same time. Okay, so we've got these two probability spaces. How is this the same as this? They haven't got the same number of elements. Well, oh no, you can't see it now because of the glare of the sun. Okay, okay, that'll have to do. Right, okay, so how is this the same as this? Well, it's kind of the opposite of conditional probability. In conditional probability, what we did is we took an event and we said, let's call that the whole sample space, and let's do probability relative to this new sample space, and that was conditional probability. In this case, what we're going to do is we're going to take an event and we're going to say, we're going to demote it instead. Instead of promoting it up to being a sample space, we're now going to demote an event to being an outcome. So we're going to say, let this event be an outcome. Let that be the outcome that you get a heads on the first, well, it's the event that you get a heads on the first one, and this is the event that you get a tails on the first one. But now let's say they're outcomes, then I can map I can map that onto here, and I can map that onto there. So I map, in essence, what I'm doing is mapping both of these outcomes onto this outcome. And then it's the same thing, because look, this is just the outcome that you get a heads first time, and this is just the outcome that you get a tails the first time, and they are the same thing, but in a sort of more, they're not the same thing in the same way as they were last time. They are not an isomorphism, they're not as strong as that, but they are what is known as a homomorphism, which is a more subtle concept. It's saying that if you zoom out almost, and you view these now just as outcomes, then this structure is embedded higher up in this probability space. Okay, so when we look at this, if we look at the probability of this event is going to be a half, and this event is, well, sorry, no, it's going to be, it's going to have some probability p potentially, and this is going to have probability 1 minus p, and again, that is going to be distributed in the same way as a Bernoulli p distribution. Oh, sorry, it's not, use the word distribution again. It's going to, it's the same probability space as a Bernoulli p space. We will define distribution in the next video. So it's in a sense the same probability space, but it's not. It's saying that this probability space has this structure of the Bernoulli p space within it, in some sense. So now let's go for the rigorous the proper definition of what a random variable is. So a random variable. Start again. I'll write bigger so that you can see it. A random variable is a function, so it's a function phi, which maps your probability space, what specifically maps the outcomes of your sample space onto the real numbers. So for instance, in the first example we had, where we had the heads and tails, it was mapping the outcome that you got a heads onto 0, and it was mapping the outcome that you got a tails onto 1. So it mapped it onto the real numbers, and such that any event, well, this is what's difficult. You have to have a distribution on the real numbers. So what you want is, basically what we're going to spend a lot of time doing is we're going to be looking at standard probability spaces, of the real numbers, and the Bernoulli p space is an example of a standard, one of these standard probability spaces that's in the real numbers, and loads of other probability spaces are exactly the same as them. So we might as well just study that one in the real numbers, and then we've solved all of them. Another one we'll mention in the end of this video is the binomial probability space, and we'll show how that is a probability space on a subset of the real numbers, and how many other probability spaces are the same or isomorphic to it, meaning that you can find a random variable that's going to link them. So basically we're going to make probability spaces out of the real numbers, in the real numbers. So the outcomes, so when you take your sample space, so let's say this is omega prime rather, it's a subset of the real numbers. So you take your outcomes, they're just numbers now, they're going to be represented by numbers. So in effect, all you're doing with a random variable is you're just relabeling your outcomes, which could have been whatever, as numbers now. That's the concept, really. But you want the probability space structure to remain the same. So that is what a random variable is. It's a way of, that's the best way to view it. It's just a labeling. It's just a way of attaching a labeling to your probability space. So you just label the outcomes by a number. Now it's more powerful than that, because when you do that, you realize that loads of probability spaces are actually all the same probability space in the real numbers. They're all isomorphic. So you just need to study one, and you get the answer to all the others. Okay, so we make probability spaces in the reals. So these probability spaces will have they'll have elements of real numbers, and they'll have events on them. So event bar, and they'll have probability bar, and you basically want any event in here to have an event corresponding to it in here, and you want the probability of an event in here to be the same as the probability of an event in here. That's what you want. So in actual fact, I think the best way to view a random variable is that it is just a way of labeling the outcomes of your experiment with numbers. Okay, so we'll now look at the such that, so I just want to finish this definition, such that for any event is an element of f prime, there exists, the pre-image of E is an element of f, and such that the probability p prime of E is equal to probability of the inverse image of the event, basically. So any event you have, in this space has to have an event corresponding to it in the previous space, and the probability of an event in this standard space has to be the same as the probability of that event, of the inverse image of the event in the initial space. So let me show you why this is still a random variable, because this if we were going to make it an isomorphism, then we do it the other way as well, i.e. any event in the initial sample space has to have an event in the final real number probability space, and the probability of any event in there has to be the same as the probability in there. It's only one way at the moment. It's saying every event in here has to have an event corresponding to it in there, which is the subtlety of why things like this are still random variables. It's basically not the definition of an isomorphism, it's the definition of a homomorphism. It's saying that they are homomorphic. Okay, I don't actually think that this probability fit. Well, yes, no. Continue on. Okay, so let me take any event in this Bernoulli P space. So this is a Bernoulli P space. So there are only 4 events we know. There's the empty set. Well, that's pre-image has the empty set, so that's certainly an event in here. Then there's the event containing the outcome 0. That's pre-image is this event over here, which is an event in this probability space. Similarly, there's the one containing 1, which again maps onto this, which is an event. So its pre-image is TT and TH, which is the event that you get at tails first. And then you can take the event containing 0 and 1, and that will give you the entire space, basically. So yes, it satisfies that. And again, this has probability P, this has probability 1 minus P, so the probabilities, again, are exactly correct, and the probabilities of the empty set and the whole space are correct as well. So you might ask, but surely I have in this space the event tails and heads, and that has no event in here corresponding to it, because, well, you could take its image, and its image indeed would be 1, but it somehow doesn't seem great, because, you know, you had this, what happened to tails? Why didn't you have to do that as well? And the thing is that every event in here doesn't have to have its own individual corresponding event in here. This one's corresponding event is this, and yes, it's the same as the bigger set of TT and TH, but that doesn't matter. It's still a random variable, and if that's the case where you have outcomes that aren't in perfect correspondence, if it's the case that it's also a finite probability space, then you can be pretty sure that it's not an isomorphism and instead a homomorphism. So I hope that you have understood that concept, that there are lots of different probability spaces and they might have different outcomes in their sample spaces, but as far as the probability space structure is concerned, they are either the same, either isomorphic, or they are one's kind of a bigger version of, it's kind of a more detailed version of another, and if you sort of zoom out you can it has the same structure as the other, i.e. they're homomorphic. Those aren't words generally used in probability, they're concepts from algebra, but the concept is effectively the same here. And they are probability space isomorphisms, or probability space homomorphisms. So let's discuss, for just as the final bit, another very standard probability space on the real numbers, which is the binomial probability space. I don't want to use the word distribution. Binomial MP space, let's say. So, this is the space that has, as its sample space, it has numbers 0, 1, 2, 3, 4, 5, all the way up to n, and it maps onto each of those. It takes each one of these. So firstly, note that in this probability space, every individual outcome is in a set on its own. So if you look at the set of events, you'll have 0 as an event, 1 as an event, 2 as an event. All the unitary sets are events. Okay, and basically it ascribes as probabilities to each of these. It ascribes n, what does it ascribe? N, it ascribes p to the power of that number. So let's say if we want to know what is the probability of the ith element, so let's say the probability of the set containing I is equal to the probability p to the power of I times 1 minus p times n minus to the power of n minus I times n choose I. And those of you who know something about probability will know why that's so important, and I'll quickly explain. So that's just an abstract formulation. This satisfies the axioms of being a probability space. This is the standard one in the real numbers. Now let me show you one that is isomorphic to that in the probability space sense, but is obviously different in terms of the actual sample space, i.e. the outcomes are different. So for instance, if you take a coin and you flip it n times, so take a coin, flip it n times, then your sample space, all the things that can happen, if I want to, all the things that can happen, if we take the, you can ask, well, we're going to make the probability space. We'll make the probability space all the possible outcomes, but we're only interested in a certain thing. We'll make the outcomes how many heads you get. So you can either get 0 heads, you can get 1 head, you can get 2 heads, 3 heads, all the way up to n heads. Obviously, we could have considered a much bigger sample space. What we could have considered is every possible outcome of flipping a coin n times, and then we would have gathered, we would have split that up into events, and there would be loads of possible outcomes. Well, there would only be one outcome, which would satisfy the events that you got 0 heads. There would be lots of outcomes that you got 1 head. So these are events now. These are sets of outcomes of this much bigger probability space, and you could go on like that and ask how many heads you get, and all of these events would then be mapped onto this. So they'd be mapped onto the standard binomial distribution. So you'd map these events onto just numbers. So you're decreasing their power. You're doing this homomorphism thing where you're saying, okay, let's consider this event just as an outcome now. So you're saying this probability space, this much bigger probability space, is homomorphic to this one, and if you do that, this structure on this probability space is the same as the one on the standard binomial NP space. And the reason for that is, if you want to know, firstly, let's agree that every possible outcome you get, so for instance, you could get heads, tails, 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 all the way up to heads on your nth one. So this is 1, 2, 3, 4, 5, all n throws. And that is an outcome. So you've got every single possible combination you have there. You have 2 to the power of n possible outcomes of that experiment, and each one is equally likely. So each outcome is sitting in a set on its own as an event, and the probability of that event is 1 over 2 to the power of n. So all you need to figure out is how many, sorry, no, it's not. It's not. You have to tell me what the probability that you get a heads or a tails is. So tell me the probability. Oh, that makes it far more complicated. No, I've messed this up. Each of these outcomes, the probability that you get a head is not equal to the probability that you get a tail. So let's let P equal probability that you get a head, so the probability of getting a head, and let 1 minus P equal the probability that you get a tail. Then, did I put this? Oh, right, yes, that's fine. Okay, basically, if you want to know what is the probability of a certain outcome, then you need to work out how many heads it had and how many tails it had. So you'll do P to the number of heads it had, so let's say I is the number of heads it had, and 1 minus P to the power of n minus I for how many tails it had, and you then need to work out how many possible ways could you get that, and that's just how many ways can you rearrange the heads and the tails. So that is going to be equal to n choose I, because you get I heads and you get n minus I tails, and the number of ways to rearrange those things is n choose I. So that is the total probability that you get I heads and n minus I tails. So that is the probability of these overall events. So let this be the event that you get I heads. So when you demote the overall event that you get I heads to an outcome that you get I heads, then that's that mapping that takes it onto that standard probability space, binomial NP probability space, is what is known as a random variable. So the mapping is the random variable, even though the motivation for where that word came from is that you have all these random probability spaces which are all effectively either the same, isomorphic, or have that structure higher up in them, homomorphic. And that's the concept of a random variable, and we will see the binomial probability space a lot more